All right, so welcome to the Astronomy Problem of the Day series. Today we're going to be talking about cosmological expansion of space due to dark energy. So firstly, why does the cosmological expansion cause galaxies to move far apart while leaving the distance between New York and Tokyo unchanged? And then secondly, looking at the critical density of the universe, at which the universe is balanced in its expansion. That might give you a hint to the first part as well. But yeah, so thinking about cosmological expansion, a good analogy is a bunch of people standing in a field all running away from each other. Think about Jay in the center of a field and me running out. I am 100 meters away, currently moving at 50 meters per second. Fei Lane, 200 meters away, currently moving at 100 meters per second. And if we assume that we've all been going at the same speed the whole time, we can calculate how long we've been moving, right? Because distance is rate times time. So we can say that we've all been moving for about 2 seconds if we all started at the beginning, at the center at the beginning. So then we can plot this on a line, on a graph, right? We have distance versus recession velocity, and the line will have slope 0.5. Interestingly, that's going to be the inverse of the amount of time we've been moving. So that's not a coincidence. We can look at this in terms of galaxies all moving apart too. So if we think about the start of the Big Bang, we have galaxies all moving apart from some arbitrary center. And if we plot this on a distance versus recession velocity graph, we see that galaxies are approximately moving apart from each other at 70 kilometers per second per megaparsec. Now, we're not going to get a perfect fit because there's other factors that are influencing galaxy movement, like gravity and rotation, but we can still find this approximately because over large distances, this Hubble law expansion is what is driving this all. And this slope, by the way, is called the Hubble constant. It's the ratio between the recession velocity and the distance. So the question that this begs, though, is are we actually at the center of the universe? And all we have to do to find that out is just shift perspective to see that we really aren't. Something that scientists a long time ago thought, well, if you just look from my perspective, you'd see everyone moving away from me. So if we draw the circles a bit differently, we'll see that I can be at the center too. I can see everyone in all the galaxies moving away from me at the same rate. So we're not really at the center of the universe. The universe actually has no center because it's infinite. So looking at a different force, however, gravity, that's going to be an inverse square law, where gravity is much stronger for objects that are relatively close to each other. Unlike, say, the Hubble law expansion, which isn't really a force, but it causes galaxies to move apart faster when they're much farther away from each other. So when you have objects that are really close, even on the order of galaxies, like, for example, the Milky Way galaxy and the Andromeda galaxy, they can be held fairly close to each other by gravity despite dark energy. And that's all because of this inverse square law, where the force drops off very quickly with increasing distance. So, for example, the distance between New York and Tokyo isn't actually changing because of gravity. It's causing the Earth and all the locations on it to stay close to each other, despite the long-range expansion of space. So onto the critical density of the universe. So we can, at a certain critical density, it follows mathematically, as we'll see, that all particles and galaxies in the universe won't be moving away from each other or contracting. And we want to find this critical density P sub c. But we should know that if we have a critical density that's going to be greater than the present day density of the universe, so if our present day density is smaller, that means that we're going to have this open universe that ultimately leads to infinite expansion, and we have a cold death. But if we have a closed universe, if we have a much greater present day density, then it'll eventually all contract by gravity, and we'll get to this big crunch, which is kind of the opposite of the Big Bang. If you think of the Big Bang as the start, as the first birth from a singularity. So then how do we calculate this mathematically? It seems a bit hand-wavy, but I promise you it works, and it is consistent with most observations, as we'll see. So you model the universe as an infinite sphere expanding from an arbitrary point, and you consider the kinetic and potential energy of a particle of mass m at a distance r from the center point. So first, just think about the Hubble law. We have V equals h naught times r. And then we can calculate the kinetic energy by a standard method, 1/2 mv squared. So we have that Ke is going to be 1/2 m h naught squared r squared. So that's simple enough, thinking about just the energy due to speed. Now let's think about the energy due to force, the potential energy. And to do that, we're going to need the mass. Because the gravitational force is going to be dependent on some mass. But how do you calculate the gravitational force due to everything in the universe? Well, Newton's shell theorem is actually really helpful here, which says that if we have some object on a sphere, we, for one, don't have to worry about the mass of any objects outside by a bit of geometry, as long as the outside sphere is uniform, which we're assuming space is at long distances. But then anything inside the sphere, we can all reduce to all of that mass at a point in the center. And again, due to a clever bit of geometry, so we can just think about all the mass inside of this radius r. So the volume inside of this radius r is going to be 4/3 pi r cubed. So then multiply this by the density that we've assumed, and that brings in that term, and we get the mass. So then by Newton's law of gravity, we have F equals big G, big M, m over r squared. We can integrate this or just use the formula to find the potential energy due to gravity, which is going to be negative in this case, because we're just doing is energy at the borders of the universe. We plug all this in, and we get this nice expression for the potential energy of gravity. So now we just have to set the sum of those to 0, and since the gravitational force. So now it's just algebra. We plug all this in, and we nicely get two terms. We do a bit of algebra, and we end up with mr squared on both sides of our equation. Factors that we chose about our particle don't really matter. It all ends up canceling, and we solve for p sub c, and we get that it's 3 times h naught squared over 8 pi g. So what does this mean? Well, all we have to do is plug it in with the correct units. Use units of inverse seconds for h naught. That's just going to be equivalent to the 70 kilometers per megaparsec definition, and then the standard units for g. We plug all this in, and we get that p sub c is up 9 times 10 to the negative 26 kilometers over meter cubed. And that's going to be a measure of density because it's mass over volume. And just for some comparison, that's about 5 hydrogen atoms per cubic meter. So that's not very dense, but it makes sense given that the universe is really mostly empty space. So when you average that out with the very massive stars, you get about this. And one more interesting note as well is that the observed density of the universe is actually much less than this, which gives evidence for dark matter, because given that we haven't really observed dark matter directly, or at least through our normal means, then we think that dark matter will have to make up